You see these headlines all the time, right? A new drug slashes your risk, or a study proves a treatment works. We're constantly bombarded with this stuff, but what does it actually mean? Well, to figure that out, we have to look past the hype and dive into the numbers. So today, let's pull back the curtain and find the real story behind medical statistics. So here's the game plan. First, we're going to talk about why significant doesn't always mean what you think it means. Then, we'll introduce our hero for today, effect size. After that, we'll get our hands dirty with a real-world example to understand risk and ratios. We'll zero in on the one number that gives you the clearest picture. And finally, we'll give you the tools you need to see through any medical headline that comes your way. All right, let's dive right in. Section 1 is all about tackling one of the biggest points of confusion in all of medical research. We hear that a finding is real or significant, and we think, wow, that's a big deal. But a real effect is a completely different thing from an important effect. I mean, you see a headline like this, and it sounds fantastic. Who wouldn't want that? But the phrase cuts risk is so vague. Does it cut it by half? Does it cut it by 1%? By a tiny fraction of a percent? Answering that question is what this is all about. And this brings us right to the heart of the matter. It's this constant tug of war between two different ideas. Over here, you've got statistical significance. That's just asking, is this result real, or is it just a fluke of random chance? But over on the other side, and this is the one that actually matters to us, is clinical significance. And that asks a much simpler question. Okay, great, but does this effect actually make a real, meaningful difference in a person's life? For decades, the gatekeeper for all of this has been the p-value. You've probably heard of it. A p-value of less than 0.05 is the classic gold standard to say a result is statistically significant. But here's the catch, the dirty little secret of the p-value. It's really, really influenced by the size of a study. If you have enough people, you can find a significant result for an effect that is just ridiculously tiny, practically useless. The p-value tells you the effect is probably real, but it never, ever tells you if it's big enough to actually matter. So if the p-value isn't giving us the whole story, then what does? Well, this is where our hero, effect size, makes its grand entrance. Effect size is, exactly what it sounds like. It is a measurement of how big the effect actually is. It measures the strength, the magnitude of what's going on, and it doesn't get fooled by a huge study size. It cuts right through the noise and answers that one essential question: how much does it matter? This quote just nails it perfectly. A significant p-value is just your ticket to the game. It's necessary for sure, but it's nowhere near enough. Before any doctor is going to change the way they treat their patients, they have to know the magnitude of the effect. They need the effect size. So, how do we actually measure this thing? Let's get practical and walk through the most common ways, and we'll use a single, straightforward clinical example to keep everything clear. Okay, so imagine a big 5-year study for a new heart medication. In the control group, the folks who did not get the new drug, 20 out of every 100 people had a heart attack, so a 20% risk. Now, in the treatment group, the ones who did take the new drug, only 12 out of 100 had a heart attack, a 12% risk. Simple enough, right? The most direct, no-nonsense way to look at this is what we call the absolute risk reduction, or ARR. It is simply the difference in risk between the two groups. It tells you the actual real-world drop in risk percentage points. And the math is as easy as it gets. 20% minus 12% gives us an absolute risk reduction of 8%. So what does that mean in the real world? It means that for every 100 people who take this drug for 5 years, 8 fewer of them will have a heart attack. That's the actual difference it makes. But hold on. There's another, much more dramatic way to frame these exact same results. It's called the relative risk reduction, or RRR. And the key word to focus on here is relative. This metric isn't looking at the simple drop. It's looking at the reduction as a percentage of the original risk. So here's how it works. We take that 8% reduction and we divide it by the original 20% risk. And what do we get? A 40% reduction. It's the exact same data, but a 40% reduction in risk sounds way more impressive than an 8 percentage point drop, doesn't it? And that leads us to this very critical question. Why do you think drug companies and news headlines just love to report the RRR? Well, because it almost always gives you a much bigger, much more impressive sounding number. It's fantastic for marketing. You'll also see something called the odds ratio, or OR. It's a little different from risk. It compares the odds of something happening in one group versus another. So an odds ratio of 3.9 means one group has almost 4 times the odds of something happening. It's another way to talk about the strength of a connection. And then there's the hazard ratio, or HR, which you see all the time in long-term studies, like in cancer research. An HR of 0.70 means that at any given moment during the study, someone in the treatment group had a 30% lower chance of the bad event happening right then and there. Okay, so all of those ratios are really useful for researchers, but for the rest of us, for doctors and patients trying to make a decision, I think there's one number that is by far the most intuitive and practical measure of a treatment's real-world impact. And it's called the number needed to treat, or NNT. This tells you, in the simplest possible terms, how many people you have to give a treatment to in order to prevent just one bad outcome. It's an incredibly powerful way for doctors and patients to weigh the real pros and cons. And you're not going to believe how simple the calculation is. It's just 1 divided by the absolute risk reduction. So for our example, that's 1 divided by 0.08, which gives us an answer of about 13. And here is the big payoff. This one sentence tells you everything you need to know. You need to treat 13 people with this drug for 5 long years just to prevent one single heart attack. Suddenly, that 40% risk reduction headline feels a whole lot different, doesn't it? This puts the benefit right into a human context. So let's put it all together. What did we learn today about how to read between the lines of all that medical news? Here's your takeaway toolkit. First, always look past the p-value. Demand to know the magnitude of the effect. Second, be really skeptical of that big, flashy relative risk reduction number. Always ask for the absolute risk reduction. Third, if you can find it, the number needed to treat tells the clearest, most practical real-world story. And finally, always remember that the same exact data can be spun to tell very different stories. So the next time you see a headline making some dramatic claim about a new treatment, you'll be able to stop, take a breath, and ask the one simple, powerful question that truly matters most. Yeah, but what's the effect size? Because now you know that's where the real story is.